Mark? It was just a clarification.
Yeah, sure. Go ahead.
Well, it asks for the rate, I believe. I have to find it again, but it asks for the rate at a certain point in time.
Oh, which one? Is this another problem?
Yeah, it's number 15.
15, okay.
And this one seems kind of silly because if you look at the point in time that it's asking for, the concentration would be negative because it's used up. So wouldn't the rate be 0?
No, but I'm glad that you asked about this question. After our discussion yesterday, someone had asked about this too. All right, so for this problem, let me shoot that off to the side, number 15, and let me open up somewhere where I can write. Okay. All right. Now let's read this problem. It says this reaction A goes to B, C is known to be 0th order in A with a rate constant of that value at 25 degrees. An experiment was run at 25 degrees where the initial concentration was that. After 5 minutes, the rate is. All right, so they tell me right off the bat that the rate law is 0th order. So what does that mean? Let me see. That means that the rate equals K times the concentration of A to the 0th order, 0th power, right? So what does it mean when you have something to the 0th power? What does that equal?
It has no effect on the rate. That's right. So it wouldn't deplete. Actually, it wouldn't do anything. It would have no effect.
You are right. So it means that the rate equals K. They gave you K in the problem, so the rate is K. And it doesn't matter what you start with and what time it is, it's always the same rate for 0th order. So it's kind of a trick question.
Okay, I thought that's what was going on, but I wanted to make sure I understood it fully. Thank you.
Yeah, you got it. Any other questions?
I'm good on my questions now.
All right, well, keep them coming. And thanks for asking. So I take it that everyone's going, we're doing great with time. You know, I have discussed the notes. We're almost finished the first chapter for discussion. And the next thing we're going to do is equilibrium. And I have built into our schedule 2 extra days to go over stuff the week of the exams. So, you know, if you have any questions that you want to hash out, don't think that you're going to slow us down or anything. We're going to get through the material in no time at all. So anyway, I guess what we can do now is maybe take a look at the notes and go over some of the stuff that we talked about yesterday in discussion, and maybe go on to new stuff, unless there's some objections. Okay, so we're good. You guys want to do that?
Yeah, I think we should probably go over some of yesterday's stuff because some of us weren't here.
Okay, well, not, you know, I tape these and I post them in the same section that you went.
Right.
Yeah, so if you get any time, you should go back and check them, because then you can, you know, rewind them and take a look at them again. But anyway, yeah, I can start from the very beginning and do a quick synopsis of the whole class so far if you want. And it'll kind of give you a forest from the trees view. I'm just going to do it real quick. And just like before, if you have any questions, just holler.
Okay.
So okay, cool. So real quick, I'm going to go through these slides. This is pretty much the first slide with any info. And it's for the kinetics chapter. We wanted to look at how reactants come together and form products, specifically how fast that happens. And that's chemical kinetics. So we said, well, geez, it really matters. Number one, the nature of the reactant, what's reactant? If it's a radical reaction, that's going to happen very fast. If it's an acid-base reaction, probably not as much. If it's a combustion reaction, probably fast. So the nature, of course, of the reactants is going to come into play. But there's other important factors that scientists like to model when it comes to chemical reactions. And so we named some of the other important ones, but there's, millions of different ones. But in a freshman general chemistry class, we just take on a few, and that kind of gives you an idea of the mindset that goes on when analyzing reactions and how fast they take place. So those other ones were the reactant concentration, the temperature, catalyst, and surface area. Surface area, we're not going to do too much on. It's a physical state. The more surface area you have, generally, the faster the reactions go. But the other ones, 2, 3, and 4, are the ones that we're going to look at in some detail and try to fit to mathematical equations that will allow us not only to understand data that's taken in the lab, but also predict data in the future for experiments that haven't happened yet. And that's the power of modeling with math. Okay, so we introduced that and we said, okay, let's take a look at how we can get an idea of how we apply rates like miles per hour, meters per second, when you're running or something to chemical reactions. We said, well, we got to look at changes of atoms within time. And we define what those deltas were. Mathematically, it's always final minus initial. And we took a look at how you can represent that in graphs, in tables. And we also said, well, a lot of times we don't look at molecules, we look at the concentration and how that changes, but it's the same thing as moles or molecules per time. We just divide by a constant factor of volume, liters. So that's no biggie. And we talked about that. We talked about instantaneous rates and how that can be approximated without calculus by finding the slope of a tangent to a curve. And so we also introduced this generalized equation that helps us relate the rate of a reaction to the rates of consumption or production of any of the products, which we just talked about a little bit. So you should go back and study what these guys mean in terms of words. And also sometimes in problems, if they say consumption, then that negative sign in the math is assumed. And production, you don't have the negative because these deltas are going to be positive. There's an increase in the product concentration. Then we looked at a few specific examples. And then we introduced the rate law. The rate law is our attempt to mathematically model that the second item here, the second quality that affects reaction rates. How would concentration affect it? And can we mathematically model that? We said, yeah, we can do that with the rate law. So the rate law, what was interesting about the rate law is it shows how the rate of a chemical reaction changes when you just change the concentration of the reactants, leaving everything else constant. And that goes into what makes up K, the rate constant. So it changes that the rate is proportional to the concentration into the rate equals some constant as long as you keep everything else fixed. Then you can mathematically model it in that way. So we talked about how to go about finding those power dependencies of concentration on rate using a bunch of experiments with different concentrations of the reactants and their corresponding changes in rate, if any. And so we saw how that connection between the experiments and the rate law can be made to come up with these rate laws. We also mentioned that K, this weird thing, the rate constant, has units that change so that rate always comes out in molarities per second. All right. And like I said, I'm going fast here. If anybody has any questions, just say, hey, wait a second, hold the phone. I'm not too sure about this. Can you clarify it a little bit? But anyway, we took a look at how concentration and time would change for the three power dependencies that general chemistry students usually run up against, even though these orders that we call can be anything. They can be negative. In the case of a retardant, you add in that and it slows down the reaction. And it can be fractional. So we're just mostly concerned with 0, first, and second order. And we also looked at how the rate would change with concentration. And in that problem that we just looked at, you saw that for 0th order, that rate is independent of concentration. I don't care what the concentration is, that rate is always going to be the same. Okay. We took a look at how to take those rate laws for different experiments and just take ratios of those. And with those ratios, we can also figure out what that order dependency is, whether it's 0, first, or second order, by taking these ratios. And sometimes it's easier to do that when you're using experimental data that doesn't exactly double or triple a concentration, you know, and it's not as easy to see. So there's examples here on how to use those rate laws and with answers. Okay. Yesterday, we started talking about integrated rate laws. So if you looked at the video from yesterday's discussion, this is pretty much where we started. So we said, okay, we got a pretty good understanding of how rate is affected by changes of concentration, but is there any way that we can track the change in the concentration as a function of, say, time? And the answer is yes. It's called the integrated rate laws. And so we looked at these integrated rate laws yesterday for 0th, first, and second. This column we mentioned, that is what the rate would equal for these different rate laws. And this is the associated integrated rate laws that go hand in hand with each one of those rate laws. These guys were derived through integration, and we talked about what each one of the terms meant yesterday. So for example, this first guy here, this concentration of A at time t, that's what that subscript T means. So I have an initial concentration of A at time equals 0, that's when the experiment starts. What will the concentration be sometime in the future at time t? Well, that's found equal to that time t in the future times the rate constant for 0th order type reactions. For first order type reactions, it's a log function that relates the initial concentration to that concentration in the future. And for second order, it's an inverse relationship. Notice no negative here, but negatives here and here. And we mentioned yesterday that all of these integrated rate laws that are derived from the rate law pretty much tell us how the concentration changes in the future for any possible time. So these are really, all of these are what I called infinite point functions. So you pick the time, and I'll tell you what the concentration is. I don't care what time, anytime. Infinite point functions, right? Another way to look at it is the dependent and independent variable, or y equals mx plus b. Okay, where y, as you know, is the dependent variable, and that depends on x. You pick an x, I'll tell you what y is. So we made that relationship. Now, once you make that relationship, you guys should know from your math background that that's an equation of a line. So we went and connected what we were talking about yesterday to the lab, that first lab that you're doing, the online activity uses the integrated rate law. And also when you come in here, you're going to be using some of that as well for the first kinetics lab. And then we said, okay, well, these guys are infinite point functions. One of those points in these functions is very important, and that's called the time, t, that it takes to cut the initial concentration in half. So this is the associated half-life. And the way that you get this equation, T1/2, that's the half-life, or the time it takes to cut that initial concentration in half, is found equal to these different bits for 0th, 1st, and 2nd order. And so the way these guys were derived is they just took this infinite point function and they just substituted in that that t becomes T1/2. That's one particular time, and I put the t on the other side of the equation as T1/2, and then I just solve for that. Now at T1/2, that's when this T1/2 equals 1/2 the initial concentration. So yesterday I did that substitution in, I think, the first two equations, and I showed how these guys were derived. So you might want to take a peek at that, unless you can do that right now. All right. So once we introduced that, I said, okay, for you guys out there who know calculus, the way that these integrated rate laws were found was through integration. We said that we know that the rate equals this change in A over T. We also know that if it's a first order, then the rate should equal that as well. So I can equate those two like this. I can clear my like terms, bring T over here, bring concentration over there. Then I can use calculus to integrate that through concentration and time space. And voila, I get this integrated rate law, which now tells me how concentration changes in time. So the integrated rate law, whether it 0, 1st, or 2nd, always does this. It tells you how concentration changes in time, whereas the rate law tells you how the rate changes according to concentration changes. So you can see that the rate law is different. It's more, it deals with the rate and the effect of concentration on it, whereas the integrated rate law talks about how concentration changes in time. So you kind of get a little bit of different information from one and the other. So we talked about how they would behave yesterday in different situations, how you might calculate them. We talked about radioactivity being first order integrated rate law, and that the half-life for first order processes are concentration independent. whereas the other two have concentration involved. And that comes into play in carbon dating and things like that, which we'll get to at the end of the term when we talk about nuclear chemistry. This is the integration for second order, and it shows how that integrated rate law comes out from integration. And again, we start back here by equating the change or the rate of change of the reactant to the rate law. Okay. And then we went on to say, okay, we're going to go on to something a little different now. We talked about the integrated rate law, but now we want to shift gears a little bit and talk about this rate constant. So here we have the rate law that we've studied for a week or so. And we know that the rate of a reaction is sometimes connected to how concentration of the reactant changes, as long as we keep everything else fixed. And that is surface area, we don't add a catalyst, we don't change the temperature and anything else. Just constant, we just allow concentrations to vary. That's our rate law, right? That's what we call the rate law. But now we want to take a look at and maybe dissect that rate constant and see what's in here. You know, can we change things? If we change anything, how does that affect the rate law? So we introduced this slide that shows for this reaction here, it shows how the rate constant changes with temperature. See, it's not a constant. So if you change temperature, the rate constant changes, and at least for this reaction, as temperature increases, the rate constant increases drastically. So what does that mean as far as the rate? What happens to the rate when I increase temperature? Anybody out there? Wow, you still paying
It goes
attention?
up as well.
Yeah, thanks. I never know if anybody's out there. Maybe I'm just talking to myself. So yeah, it goes up as well, because as temperature goes up, this changes, it increases, and you can see that increase. As temperature goes up, it goes up. And if the rate constant increases, then the rate has to increase. So the next part of the bunch of slides we're going to look at is figuring out what's in that rate constant that makes it change with temperature. So that's what we want to understand next. And we want to understand it, as usual, conceptually, picture it in our mind, but also mathematically. Oh no, I hate math. Yeah, okay. I don't hate math. I like math, but if I go to a party or something and somebody says, hey, what do you do? I teach chemistry. And they're like, oh, I hate chemistry. Never liked the math. So I get it. I get it all the time, actually. So anyway, in order to understand how the rate constant changes, what we want to do next, and what your general chemistry text does, and all freshman general chemistry texts do, is they introduce this very simple model called the collision model. And we talked about this yesterday too. And all it says is that, hey, for reactants to react, they have to come together, right? Or they're going to have to bang against the side of their container. And yesterday we said, well, geez, why is it that these reactants need to collide? And someone, if you watch the video, said, well, it's because you have to break the bonds in the reactants. So here I have a picture of a reaction down here where I have two big blue balls and two big red balls in the bottom and they're colliding, this could be like H2, and this could be F2 or something like that, right? And so over here we can have products of HF. So in order to break the bonds in the reactant, it needs energy. Where's it going to get that energy? It gets it from collision, and that's collision theory. So Arrhenius was one of the first scientists to look at this, and he was studying it and he's thinking about it, and he says, well, geez, every time do they collide, is there a successful reaction? Of course not. Well, then what does that depend on? You know, why isn't there a successful reaction every time they collide? So he's thinking about, well, sometimes the collision just doesn't have enough energy. So how can I represent that in a pictorial fashion? Arrhenius does that with his potential energy. Where is it? With his potential energy curve. Here we go. So we have energy on the y-axis versus reaction pathway. So this reaction, if I look at the reactant, it starts here. This is my reactant, and this is my product. So this is a unimolecular type of a reaction. It involves one molecule. So this molecule is probably bouncing off of the container or maybe hitting another molecule to give it enough energy. But anyway, you see that they're different molecules because the nitrogen here in the reactant is connected to the methyl group, CH3. But in the product, the nitrogen is connected to the carbon and the methyl group is way over here. So it's just a rearrangement. This bond needs to break and this bond needs to form to make the product. Arrhenius says, okay, well, they collide. That gives it enough energy. So when the molecules collide, they rise up in energy to a maximum, or this maximum in this potential energy curve is related to the minimum amount of energy needed for reaction. He calls that minimum amount of energy the activation energy, or EA. So any other energy will take this reaction over the hump with no problem. So EA in this picture is the maximum, but it's the minimum amount of energy required. So sometimes that's confusing. But anyway, what is happening pictorially, can I look at the molecules and say, oh, what's happening in that molecule? Yes, I can. And scientists do that, and they call this geometry right at the top here the activated complex, or sometimes they call it the transition state geometry. So this transition state geometry is kind of like the average between the reactant and the product. And it is where the bond that needs to be broken is taking place. It's not quite broken all the way at the same time as where the bond that needs to be formed is getting formed. So I have a picture up here of the activated complex, and I see that this bond right here, dot, 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 dot to nitrogen, is the one that's being broken at the same time that this guy over here is being formed, this carbon-carbon bond. So that's the best guess that we can make of this transition state geometry. It's where there's a simultaneous breaking and forming of bonds. That would have to be associated with the minimum amount of energy required to just get over that hump. And so we talked about that, the activated complex, how you might guess what it is given any typical reaction. And that was where we ended yesterday in our conversation. So now you're all caught up in Not that much time. So any questions on that? Okay, good.
No.
If you need any
I
more
think I'm
details,
good.
yeah, good. If you need details, check out that other video from yesterday, and then by all means in the future, like next week or something, if it's still not clear, ask.
Okay, we'll do.
Awesome. All right, so you can calculate the different parts of that potential energy surface in terms of energy. So sometimes in problems, you may be asked to calculate the EA, the activation barrier. Or there's another important energy in this diagram, which we associated with in Chem 200 as delta H often, or delta E in this picture. It's just the change in the energy between the reactant and the product, right? We equated that sometimes with delta H if it was heat that was given off. And so you see in this picture that delta H is going to have what sign? Anybody want to take a guess? You got a 50-50 chance. You flip a coin. Is it positive or negative? What is it?
Negative sign.
Yes, you are correct. Very good. And it's negative, obviously, because the final, we always do the deltas final, is going to be here. The initial's up here. So the final is lower in energy than the initial, which is higher. So that's going to give us a negative value. And so we see that delta H is exothermic as opposed to a endothermic that might end up here somewhere. But in either case, note you're going to have an activation barrier. Okay. Still got to go through that barrier to break the reactant bonds. All right. So now we have this collision theory that kind of helps us picture what's going on in a reaction. And it also can explain things like when the concentration is high, the rate often is higher because there's more collisions. So the collision theory kind of predicts that. It also predicts that when the temperature is increased, those molecules are going to be moving quicker and they're going to collide with more energy. So the reaction rate should be higher, or the reaction should be faster because that activation energy is more likely going to be achieved or more at higher temperatures. It also incorporates what's called the orientation factor, and we'll look at that in a second, I think, and the frequency of collisions. That's all just from collision theory and Arrhenius's analysis of it. So let's take a look at how Arrhenius pictured that. Okay, so Arrhenius, he wants to look at a collection of molecules or particles, which has been done mathematically by Boltzmann. So he knows Boltzmann, so they talk, and Boltzmann explains to him how energy distributions can be modeled mathematically for a collection of particles or anything, billiard balls that you break, and there's balls flying all over the table. Some are not moving very quickly, or maybe they're just still. Some are moving very quickly, but on average, there's an average energy that collection is moving at. So Boltzmann explains to Arrhenius that fraction of molecules that have a certain energy can be mathematically modeled with this expression over here. F is the fraction of molecules that have an activation energy of that amount or greater. So in this picture here, this is where the activation energy is for some reaction. Oops. Okay. Um, so you can put that anywhere on your Boltzmann distribution. We just picked one because we just said, okay, hey, just pretend that the reaction has this energy, but we could have made it down here or up here. It doesn't matter. And the area under the curve, there's two curves here. You'll notice the area under each curve represents the number of molecules in the collection. This one, the first curve corresponds to the lower temperature. The second curve corresponds to a higher temperature. So Boltzmann is telling him, Arrhenius, how temperature changes the curve and how it comes into the mathematical expression. And he says, at lower temperature, on average, your molecules have this energy, this kinetic energy. At higher temperature, that curve hunkers down a little bit, the peak goes down, but shifts to the right. So on average, more molecules have a higher kinetic energy, and therefore more molecules should react. Look at the area under the curves. For the first curve, it's represented by the blue. That's the number of molecules that have the activation energy at that lower temperature, versus the one at the higher temperature have that plus this amount. So the higher temperature has more molecules that have the required energy or greater. And so Arrhenius says, oh, wow, I can use that in defining a new rate constant, or at least I can kind of dissect that rate constant into parts. And so let me show you the next slide. There we go. This next slide shows the effect of orientation on collision. So we're just using collision theory, and Arrhenius is putting all this together. He talked to his Boltzmann buddy, who's going to talk about the activation energy and temperature. And now he's thinking about orientation of collisions. He's using the collision model, and he's saying, well, geez, you can have effective collisions and ineffective collisions, even if they have the right amount of energy. This is also important. So here I have some reaction where I'm going to take a chlorine and I'm going to react it with NaCl. My products are going to be NO and Cl2. So I can imagine when these two reactants come together and they collide in this orientation where the two Cl's collide, that, yeah, that's a good orientation. Now, does this reaction happen? Well, that depends on other factors like the activation energy. Did they collide with enough activation energy? If not, then this reaction isn't going to happen, but at least has to collide with this orientation. Because if it collides with a different type of orientation like this, then you're not going to make these products. So it's important to look at that orientation factor as well, not just energy criterion. All right. So now we're ready to put this together and redefine our rate constant. So Arrhenius says, well, I can now dissect the rate constant into at least two parts. There's this pre-exponential factor called A, and in A, there's everything else besides the energy criterion, EA, and the temperature. And everything else, a couple of the big factors in everything else, is the correct orientation and collision frequency, how often they collide, and everything else. So if you keep somehow constant those factors, then A is our new proportionality constant, and we can split out some other terms that affect K, namely the energy activation barrier and the temperature. Any questions on that so far? All right, so now our rate law, check it out down here, where we have a rate of reaction equals the rate constant times the concentration dependency. Now we can replace that with, instead of K, we can put in Arrhenius's definition of K, and then talk about what would happen to a rate of a chemical reaction if we changed the temperature, or if we changed the minimum amount of energy needed for reaction. Now I know how I can change the temperature. I could just turn the burner on a little higher or lower. Does anybody know out there how to change the activation barrier height?
Would that be to change the temperature?
No, the only way that would happen is if you change the reaction mechanism, and we haven't gotten to that yet. So let's assume that the reaction is going to take place in the same way. So for that barrier height, for some reaction, right?
You can add a catalyst.
Yeah, bingo, we have a winner. We can add a catalyst. So now we can talk about the effects of a catalytic type reaction. Now you know that catalysts lower the barrier height. So this is the catalyzed and this is the uncatalyzed reaction here. Is there another way to change the barrier height? This is kind of a trick question. Change the reaction. All reactions have different barrier heights, but assuming that the reaction is the same, then that's pretty much the most common way, is to add a catalyst. Okay, I just wanted to throw that in there because sometimes that gets confusing. If I look at one reaction versus another different reaction, like a radical like chloride reacting with H2 gas versus an acid-base reaction like hydrochloric acid and sodium hydroxide, or a combustion reaction, those guys are going to have different barrier heights. All right, different from each other, I should say. So what can we do with this? All right. Now, what happened here? This is another form of the Arrhenius equation. Okay, where did that come from? Let me show you where that's derived from. I think it's interesting. So Arrhenius says K equals A times E to the minus EA over RT. By the way, what's R? What's this R? Anybody? That's not the rate.
8.314.
Yeah, that's the
Is that
idea.
the-
Go ahead.
I was gonna say, is that like the Reidsberg constant? I can't remember exactly.
Yeah, no, that's not it. See, there's a lot. That's another problem with chemistry. We use all these symbols, and a lot of times they mean different things in different applications. So it's not the Rydberg constant that gives you the energy for an electronic transition in the hydrogen atom.
It's the universal gas constant.
And bingo. Now, that universal gas constant has different units. So it was 0.831 liter atmospheres per mole Kelvin or something like that, right? I think it's that 0.0821, maybe 21. I don't know. But anyway, if I change from these units to these units, then the number changes from this to this. Now, why would I want to use R in these units is because I'm using an activation barrier, probably in units of joules. So I have to have consistent units. So when you use the Arrhenius equation, you use the R in this unit, okay? All right, so this Arrhenius equation, if you look at it just for one particular reaction, right? Just say sodium hydroxide plus hydrochloric acid gives water and a salt. Then the activation energy for that particular reaction is what it is, as long as you don't add a catalyst. So that doesn't change. EA does not change. So what can I change? Well, one thing I can change is temperature. So I'm going to put a little index here, I, and I'm going to say every time I change the temperature, what's going to happen to K? It changes. So again, this is like an infinite point function. All right, but I don't like the way it looks because it has this E in it. This inverse log function E. So I'm going to try to get rid of that. And I'm going to take the log of both sides, natural log, ln k, and I get rid of that. And this is like two different terms. I use a law of logs, and I get this factor, RT, plus ln A. So that's what I get when I take the log of both sides and do a little massaging, a little mathematical massaging, move stuff around a little bit. Now, what's the advantage of this form over that one? Well, again, this is an infinite point function where the y is associated with ln k, that's the dependent variable, and the x is associated with 1 over t, which makes the slope and the intercept associated with what? Anybody? What's the slope equal? Therefore, m equals no mathematicians out there? Or you're just being shy?
Would it be EA over R?
Yep. And B, of course, equals ln A. So now if I do an experiment where I change the temperature and I calculate K, then I could take ln of the Ks that I find experimentally, and I can plot that 1 over T, and I know I'm going to get a straight line. And that slope of the straight line is going to equal this, and the intercept is going to equal that. So experimentally, I could determine EA. And I can determine that pre-exponential factor that is associated with the collision frequency and the correct orientation. Pretty cool, huh? Yes, that's very cool. I don't know if you guys share my enthusiasm for that, but anyway, you're going to probably be getting into this. And I think one of the experiments that we have for you guys to do in lab deals with making plots of a few of the Ks versus 1 over T, and it'll allow you to calculate the activation barrier for that reaction. Just one more thing while we're here, I'm going to ask you guys. For this particular representation, is the activation barrier positive or negative?
Positive?
It's positive. And why does it have to be positive?
Because does it have to do with the ln function?
Well, yeah, it does. But check out this. And this is a tough question for you guys to answer. What's the slope? What's the sign of the slope for this plot?
Negative?
Yeah. So this is going to be negative some number. And as we see over here, that's going to equal minus EA over R. So the negatives have to cancel. So I get a positive EA because you don't have a reaction with a negative EA, at least not the ones we're going to study, right? It's always positive, that activation barrier. Always have to go up to break the bonds in the reactant. Ones with maybe negative or zero activation energy might be like a radical type reaction where you don't have to break any bonds. See, this is a chlorine radical here. And so in that case, you don't need an activation barrier at all. And maybe that could be, but we don't really, in Chem 201, we don't look at radical reactions very often. And you know, maybe if you've read nutrition, stuff like that, and radicals are bad in the body because they're so reactive and they're associated with cancer causing things. So you know you don't want radicals in your blood and stuff like that. And that's the reason why. They're really reactive and they'll mess up cells and things. But what do I know? I'm a chemist. I'm not a biochemist or a biologist. So, all right. This plate goes into some of the stuff that we just talked about. And remember, this K is an infinite point function. And I have my dependent, independent variable. And when I take the log of K and I plot that with 1 over temperature, then I'm going to get a straight line with a negative slope. And so this plate talks about how those relationships can be used to calculate the EA and A, the pre-exponential factor that's associated with collision frequency and orientation. All righty. Any questions so far? So you can look through that, check out the numbers. You know, it's all the same stuff. Slope is calculated by change in Y over change in X. You see that it's negative, and it should be negative because EA is positive. Okay, so we're good. And this is a practice problem for you guys. And in this problem, it introduces the use of the 2-point Arrhenius equation, which is on this plate. In test situations, especially, we don't ask you to plot things because there's just not that much time. Maybe in this format with COVID, you could, but usually in test situations, you don't have time to make a plot with a whole bunch of points. So what they do is they say, well, let's do an approximation and just give you 1 point and then another point with maybe a question of either the temperature or the rate constant, and have you solve for one or the other. And so that's the application of the 2-point Arrhenius equation, which is just taking the Arrhenius equation twice and solving for the unknown. So you have two equations and two unknowns, so you just collapse them, and that's what you get. Now I can derive this equation for you, or you can do it yourself. Well, do you want to see the derivation of this, guys?
Yes.
Okay, it won't
Yeah.
take long. I'll show you how it goes. So the Arrhenius equation, at least that one form that we just looked at, says that the log of k equals minus EA over R 1 over T plus ln A. And let's say I have that for some temperature. I'll call that T1. So as soon as I give you the independent variable, that locks in the dependent variable as K1. And then I can do this again for a different temperature, K2. Okay, now what this is assuming, this 2-point equation, it assumes that when you change the temperature, that pre-exponential factor does not change. And that's pretty much true as long as you don't change the temperature too much. But if the temperature is a lot different, then I doubt that A is going to be the same. All bets are off. But that's kind of nitpicking for a general chemistry class. So we just assume that A stays the same. So when I subtract the two equations, one from the other, I get ln K1 minus ln K2 equals minus EA over R times 1 over T1 minus 1 over T2, and these guys drop out. Does everyone see that so far? Well, you
Yeah.
can go, yeah, okay.
Don't you need K2 minus K1?
Yeah, that's right. That's what this is. And then I can use the law of logs that says over here, and it could be ln or log. I'll use log of x minus log of y. That equals log of x over y. That's just a law of logs. And so I can collapse the term over here as K1 over K2. And there's your Arrhenius 2-point equation. So when you apply this equation, which you should do in this example in the notes, and make sure you get that answer because the answer is given in the notes, it's just good practice. The thing you have to be careful about is making sure that all your units are consistent. So if you're going to use R in those units, then the EA has to be in units of joules, and the temperature, what units does that have to be in?
Kelvin.
Yeah, don't forget that. So that's a couple common mistakes, units, when using this equation. Another mistake is making sure that K1 is put in this spot and the corresponding temperature is put in this spot. Now, some equations in your textbook will have this negative sign distributed. And what the equation looks like in that case is ln K1 over K2 equals EA over R times 1 over T2 minus T1. So you have to watch out. The equations are the same. They give you the same answers. But when you distribute that negative sign, those temperatures flip in order. Now, having said that, you can have a whole bunch of different types of problems that you can solve using the Arrhenius two-point equation. In other words, in the problem, they could give you the activation barrier of the reaction. They could give you one of the rate constants at this temperature and ask you what the rate constant is at a different temperature. So you solve for that. That could be one possibility. Or they could give you the rate constants and the temperatures and ask you to solve for the activation barrier. You know, so you see how you can mix it up using this equation for different problems. So what do you guys think about that? You're speechless. All right, what I want you to do is go ahead and try to calculate that activation barrier for this problem. The only different thing which I threw into this problem was this wording. The rate constant increases by a factor of 4.27. Now, you might not know what that means, and you should know. And so I want to explain what that means. So I have a rate constant of K1, and I have another rate constant of K2. And K2, it says it increases by a factor of 4.27. So that means K2 equals 4.27 K1. That's what they're telling you. So when you form that ratio in the Arrhenius equation of K1 over K2, that's going to look like K1 over 4.27 K1. So the K's cancel out. They don't even have to tell you what the K's are for you to solve the problem. Make sure that you convert these to Kelvin and see if you can get that. If not, we'll go over it next time, because I think you guys have enough to think about right now. Check out any of the homework problems that deal with this. And again, if you have any questions on those, ask them. I'm going to stop now, and I'm going to wait for everyone to leave in case you have a question. Is that fair?
Yes.
Okay, guys. Have a good weekend, and thanks for your questions.
Hi, Professor. Where are the videos are posted, the recorded videos?
Oh, yeah, I'll show you right now.
Okay.
Okay. So this is let's go. Okay, so here's our course. You get into the course content, and then you know how to get to the Zoom meeting. So you come into here, and right here. So that was our first one, second, third. Today's going to go right here in number 4.
Okay, thank you.
Yeah, so you just click on that, and it brings you to YouTube. I have I've been checking to make sure that they're closed captioned, and I think they are. They do it on the fly there with YouTube. But if there's any problems and you need clarification, let me know.
Sure, thank you.
Thank you.
I actually had a question about the lab because I'm in your lab class.
Okay.
I wanted to know about format for submission of the online lab
Okay.
assignment. I think I emailed you, so you can ignore that email now.
Oh, good, good.
Yeah, but in the instructions, it says to kind of